Module 3, Session 4. Session 4 will cover Learning Outcome 4.3.3. Draw Venn diagrams and complete contingency two-way tables to solve probability problems. Learning Outcome 4.3.3, Part 2. Draw Venn diagrams and complete contingency two-way tables to solve probability problems. We saw earlier that Venn diagrams help us to count outcomes when they may overlap. If we have different numbers of things and are not certain about the overlap, Venn diagrams can help us work it out. Let's take a closer look at this. The following data was obtained from a survey at a company. There are 100 employees, 90 of whom are smokers, 30 of whom who go to gym, and 20 who both go to gym and smoke. In this example, we know that there are a total of 100 employees, but it is hard to see the numbers that are not in the intersection region. So, we draw a Venn diagram and write that the total number n equals 100. We fill in the number 20 in the intersecting region. Then we can work out that because there are 90 smokers altogether, we subtract 20 who also go to gym and get 70 employees who smoke but don't go to gym. And in the same way, we work out that there are 30 minus 20 equals 10 people who go to gym and don't smoke. Let's watch a video of a lecturer using Venn diagrams to solve a probability problem.
A and B are two events in a sample space S, where NS is equal to 200, and A is equal to 80, and B is equal to 70, and A and B is equal to 40. So that's like their joint number of events. Now, we have to draw a Venn diagram to illustrate the events. This is just a skeletal form of a Venn diagram. What is important is to put fair values and demonstrate how we distribute these events. So we will agree that this is event A, and then this is event B. So this circle here, event B, this is event A, and they share this portion. This portion they both share. That's where the two circles meet. Now, if A has 80, which means that 80, we're going to have 40 here, and you're going to understand why. And then if B is 70, we're going to have 30 here. It's clear that they will then share this 40. Why do they share this 40? Because A and B. So this is A combined with B. This is where they meet. They share 40. So you can still see that this circle is A. 40 plus 40, 80. This circle is B. 30 plus 40 is 70. And they share mutual ground of 40. The Venn diagram is done. Outside of it, if you balance this is 40, 40, that's 80, plus 30, that's 110. They must add up to 200, which means that in this space then, we must have 90 outside here. Good. This was number A. Number B, determine the probability of event A. So if you see event A has possibility of 40 and 40, which is 80. But you can also find it out here, which is 80. So it's going to be 80 over total space of 200, which gives you 0.4. We get that. Then C, determine probability of A and B. We are given A and B already. A and B is 40. So we're going to say 40 over the total of 200, which will then give us, if 80 over 200 was 0.4, which is 40%, then obviously half of that is going to be 20%, 0.2. Number D, Determine probability of A or B. This is very, very important. What does it mean? It means that what we must focus on is the following. It's going to be A or B, which should be expressed as follows. It means that it's N of A or B divided by NS. Clearly, this means that we must then have this and this and this. It's either this or that. So it's either this 40 and the 30, or the 30 and what they both share. So 40 plus 30, which is 110. So it's 110 divided by 200, which is going to give us, might need aid of the calculator, that divided by 200. Use 11 over 20, which is 0.55. So which is 55%. For E, you need probability of B prime. So that's E. This is also the same as that, which therefore means that we will have to be the same as 130. 130. Why is it 130? Because we are focusing at B. So what is happening here is that we're looking at this 40 and the 90. So 90 plus 40 is 130. Which should give us, let's have our calculator here, 130 over 200, 0.65. And let's look at number F. What does number F say? Number F requires to do what? To determine the probability of just B. That's easy. B was already given as 70. So it's going to be 70 over 200, which should give us 0.35, which means it's 35%. And lastly, G. What does G say? Say compare the probability of A and B with probability of A times probability of B. These are two different things. So we already have probability of A and B, which is equal to, we did calculate that, probability of A and B, that was number C, we did calculate it here, is equal to 0.2, which is 20%. Now we need to take the probability of A, you times it by the probability of B, which should give us probability of A is 0.4. Probability of A, you multiply it by probability of B, 0.35. It should give us 0.14, which is 14%. The question is, why are they not equal? This is because the data itself is not independent. What is happening in event A is not exclusive to what is happening to event B. So these events or this data is not an independent data. So the reason is the data is not independent. That's the reason why they are not equal.
Now, work in groups to do this activity on Venn diagrams. Think about the problems you and your students experience with this section and how you would guide students to approach similar problems. Let's work through the solution to this activity together. In question 1, we are required to draw a Venn diagram to show the situation. We will then use this to work out the rest of the answers. Let's start by showing the sample space, which we label S. This is going to contain all of the sets. We can see that we need to draw sets for races A, B, and C. First, we are told that 23 learners ran in the 100-meter race and 21 did the 400-meter race. Later, we are told that 7 learners ran both the 100-meter and the 400-meter races. So we know that the intersection between sets A and B will contain 7 learners. A contains 23 in total, and 23 minus 7 is 16. B contains 21 in total, and 21 minus 7 is 14. We are also told that none of the learners who did the 800-meter race were in the other 2 races. So there will be an overlap between A and B, but set C has no intersection with the others. 15 learners ran the 800-meter race. Have we accounted for all the learners? There are 70 in total, and if we subtract 16, 14, 7, and 15, we are left with 18 learners. This answers the second part of question 1. 18 learners did not participate in any of the races. Question 2. In this question, we need to calculate various probabilities. A. What is the probability of choosing a learner at random who runs the 100-meter race? This will be the probability of choosing a learner from set A, which contains 23 learners. We divide this by the total number in the sample space, which is 70. So the probability is 0.33, rounded off to 2 decimal places. B. What is the probability of choosing a learner at random who runs the 400-meter race? This is the probability of choosing a learner from set B, which is 21 divided by 70, which gives us 0.3. C. What is the probability of choosing a learner at random who runs the 800-meter race? This is the probability of choosing a learner from set C, so it is 15 divided by 70, which is 0.21. D. What is the probability of choosing a learner who runs in both the 100-meter and 400-meter races? This is the probability of choosing a learner from the intersection between sets A and B, so it is 7 divided by 70, which is 0.1. E. What is the probability of choosing a learner who runs in both the 400-meter and 800-meter races? This is the probability of choosing a learner from the intersection between B and C. There is no intersection between these sets, so the probability is 0. F. What is the probability of choosing a learner who does not participate in any of the races? There are 2 ways to answer this. In the first method, we calculate the probability that a learner is not in set A, B, or C by applying the formula for complementary events, bearing in mind that A and B are not mutually exclusive. So, we subtract from 1 the probability of getting A, B, or C minus the probability of A intersection B. This gives us 1 minus the probability of A plus the probability of B plus the probability of C minus the probability of A intersection B. This gives 1 minus 0.33 plus 0.3 plus 0.21 plus 0.1, which is 0.26. For the second method, we can simply use our answer from question 1, where we saw that there are 18 learners who did not run any of the races. Therefore, 18 divided by 70 is 0.26. A two-way table or contingency table is another tool for organizing counts in a probability problem. They are especially helpful for figuring out whether two events, each with only two outcomes, are dependent or independent. Make sure students understand how to read a table like this. Point out to them that the row totals and the column totals add up to the same grand total. Follow these steps to calculate probabilities from a contingency table. For a row category, divide the row total by the grand total. For a column category, divide the column total by the grand total. For the intersection of two categories, divide the value recorded in the cell where the row and column categories intersect by the grand total. Remember that we can use the formula for calculating the probability of independent events to check whether two events are independent or not. Let's check whether a person belonging to the company's medical aid is independent of their gender using the information in this table. First, let's calculate the probability of event A, that a randomly chosen employee belongs to the medical aid. The probability of A is 100 divided by 210. Let's leave it as a fraction for now. Then we calculate the probability of event B, that an employee is male. The probability of B is 120 divided by 210. Then we calculate the probability that an employee is male and belongs to the medical aid by using the value in that cell. So the probability of A and B is 80 divided by 210, which gives 0.38. Finally, calculate the product of the probability of A and the probability of B. We just calculated these values, so we get 100 over 210 times 120 over 210, which simplifies to 0.27. These probabilities are not equal. Therefore, we can conclude that they are not independent events. This means that the gender of the employee is not independent of whether they are a member of the medical aid or not. Work in groups to do this activity on contingency tables and probability. A private banker at a financial institution analyzes the customer complaints received from 500 clients. The contingency table shows the distribution of the 500 clients in terms of their profession and the type of service they had complained about. Think about the problem areas you experience when teaching contingency tables and how you can work around them. Let's work through the solution to the activity about customer complaints received by a financial institution. Question 1. Determine the values of A and B. This question checks whether the student understands how a contingency table works. We can use either the column or row totals to find the missing values. So we can calculate A by using the column total 190 and subtracting 69 and 41 to get 80. Or we can use the row total of 190 and subtract 10 and 100 from 190 to get the same answer, which is 80. Similarly, we can calculate B by using the column total 110 and subtracting 80 and 10 to get 20. Or we can use the row total 137 and subtract 69 and 48 to get 20, which is the same answer. Question 2. If a client is selected at random, determine the probability of selecting a technician whose complaint is about credit card service. We are looking at someone who is a technician and is making a complaint about credit card service, so we are interested in this cell of the table. This gives us 69 out of a total of 500. So the probability is equal to 69 divided by 500, which is 0.138. Let's give our answer as a percentage to make it easier to interpret. So the probability of selecting a client who is a technician and complaining about credit card service is 14%. Question 3. Here, we want to find the probability of a client being an accountant or complaining about investment service. So we need to use the formula for the probability of two events that are mutually inclusive. In other words, these two events can have some overlap between them. So we have the probability of an accountant plus the probability of a complaint about investment service, minus the intersection between the two. Let's refer to our table. The probability of the client being an accountant is 190 divided by 500. The probability of the client complaining about investment service is 110 divided by 500. And the probability of the client being an accountant and complaining about investment service is 10 divided by 500. So, the probability of an accountant plus the probability of a complaint about investment service minus the intersection between the two is equal to 190 divided by 500 plus 110 divided by 500 minus 10 divided by 500, which is equal to 290 divided by 500, which is equal to 0.58. Let's express the answer as a percentage to make it easier to interpret. So the probability of a randomly selected client being an accountant and complaining about investment service is 60%. That brings us to the end of the probability section. The basis of solving probability problems is counting outcomes correctly. Tools such as Venn diagrams, tree diagrams, and contingency diagrams help us to visualize and organize the information effectively. We have reached the close of the module and the end of topic 4. Thank you for your concentration and perseverance.